So our linear model for the data at hand is this equation. The question now is how large errors our model makes when it predicts things. On top of this, we need the standard error in order to later do a hypothesis test on the regression model. So let us now calculate the standard error of this estimate, and we'll start from scratch using a more computationally simpler approach. Let Sx be the sum of all x's, let Sy be the sum of all y's, let Sxx be the sum of all x's squared, and let Syy be the sum of all y's squared. Finally, let Sxy be the sum of all x's and y's multiplied, and let n be the sample size, that is the number of data pairs we have, in our case 22. Let us now calculate beta hat. We use the formula at the top on the right side and plug in the values. In the end, we see that our beta hat is equal to 0.0016. Wait a sec. We calculated another beta hat previously. Now we did it slightly differently, and we got it this way too. Then we should follow this approach in the end, since it is a bit easier. Let's see what happens when we calculate the estimate of alpha. Alpha hat, that is the estimator for alpha, uses the beta estimator. When we plug in everything in the formula, we get alpha hat equaling 1.233697, which is basically what we got when we calculated it the first time. So in the future, we should probably calculate our estimates for beta and alpha this way while we're at it. So we have the alpha hat and beta hat. Let us now calculate the overall standard error. What we are looking at capturing is a measure of the accuracy of our predictions. So we have our table, but now we need to add columns to it. One column should show the results of running our model on the data point y, and thus gives us y hat. Another column should show the difference between our data point y, the first column, and our data point y hat, a final column, should square that difference. In short, we want to calculate the difference between our model and the actual data points we have, and then we square that difference. So for each data point y, we calculate what y hat is by using x, that is column 2, using our formula at the bottom. That way we know that we now get a new column representing y hat, that is our model's prediction of y. The new column is marked with a red circle. Let us now continue by taking y minus y hat to see how much the difference is between our data points we collected and the prediction our model makes. So, yet another column filled out. Finally, let us square the difference and put it in the final column. Again, yet another column filled out. At the bottom, we put the sum of that column, which in our case is 490.7342. Now, let us first calculate the uncertainty we have of the regression. As is evident from the equation, we take the square sum of difference and divide by sample size minus 2. Then we take the square root. The reason we have the sample size minus 2 is that we make two assumptions in this equation. One, the sample is representative of the population, and two, y bar is representative of the true y value. Let us now also calculate the standard error for our coefficients alpha and beta. Both of the equations use our previously calculated standard error for the regression, and now we see how much of that standard error belongs to alpha hat and beta hat respectively. In the end, we come up with a standard error of 3.296 and 0.000158 for the alpha and beta respectively. So we have calculated the standard error for alpha and beta. Let us now calculate the t-statistics for alpha and beta. We do that by dividing our coefficient with the standard error of that coefficient. A larger t-statistic indicates that it is less likely that the coefficient is not equal to 0 purely by chance. So the higher the t-value, the better, you could say. For beta, we seem to be safe, but for alpha it looks quite bad. If we look at the t-table for 0.025, that is, we have a two-sided test with alpha equaling 0.05 and 20 degrees of freedom, we get the critical values. In our case, the critical values are plus minus 2.086. We can now clearly see that beta is significant, but alpha is not since it is not in what we said in an earlier video, the blue region. Let us look at this from another angle also. Having statistically valid coefficients is good, but we have other ways to measure the quality of the model, that is, the goodness of fit. Let us look at two ways next. Using R² and adjusted R², and then look at the F statistic.